Let's work now on parts B and C of question number 3. We draw the circuit for t after 0 in the Laplace domain. In the Laplace domain for t after 0, the voltage source on the left, will be a short circuit because it's after 0, and the current source on the right appears, a current source of 4 amps. And you're asking yourselves, hey, what are you doing there? Why are you drawing some new sources in the circuit? Well, those sources, if you remember, are the initial condition sources of the inductor, the one on the top, and of the capacitor, the one in the middle. What are the values of those elements? This is for t after 0. Those are the Laplace impedances of each one of the elements, and they go 4 over S is the value of the source on the right, is the Laplace transform of 4 amps, and 5 ohms for this one, 3 ohms for this other one. This is LS, and that is S over 4, 10 over S, which is 1 over CS, and the values of the sources, well, the values of the sources, they point in the direction of the initial condition. The current in the inductor was flowing from left to right, so that's why that source has that polarity, left to right. And the value is LIL naught. And you're thinking, why are you writing 0.188 as 188? Because I will divide that by 1,000, that's why. And I'm dividing that by 1,000 because the HP50G and most other symbolic solvers, they prefer using integers. That's why. And the value of the source for the capacitor is pointing downwards, which is the direction of the initial condition. It's the polarity, of the initial condition in that capacitor. It's Vc naught divided by S. And I'm writing Vc naught as 152 divided by 1,000. And we are ready. Choose your reference node, the usual stuff as we do with M&A. Choose your node 1. And then select the branch currents and directions, except the one that is given on the far right for the current source, and we will be ready to write our one and only Kcl equation for the circuit. Once we write that Kcl equation, we can solve for V1, and you know that V1 in this case is in reality the voltage in the capacitor. Find that Vc1 as a function of S, and the poles of that function of S will be the eigenvalues of the characteristic equation of the circuit. They will tell us whether the circuit is underdamped, critically damped, or overdamped. And we proceed. Kcl currents going in only one, 4 over S. Currents leaving node 1, there are 3 currents. The one through the 5 ohm resistor, the one in the middle through the capacitor, and that is V1 plus the value of the source 152 over 1,000 times S divided by the impedance 10 over S. And finally, the current on the left, the current through the inductor, which would be V1 minus the value of the initial condition source, which is 188 divided by 4,000 divided by the impedance, the whole thing, 3 plus S over 4. And we move our party over to the HP50G. Now, not to bore you with my typing, I put the movie in 4 times its regular speed, and right after writing that equation, the first thing I'm going to do is check that the mode CAS menu has all the radio buttons cleared. But before doing that, I'm going to change the independent variable, which is x right now, to v1, because I want to solve for v1 in that equation, and you know how to do that exactly this way. Edit that, change that for v1, and accept the change, and we are ready. Symbolic solver. Now that v1 is the independent variable, we go to the symbolic solver, and f5 will solve for independent variable. That is v1 in the Laplace domain. That is also the voltage in the capacitor. Check out what are the roots of the denominator, the poles of that transfer function. What are they? Well, let's write the corresponding vector and find out what they are. Look what we've got there. 3 roots, 1 0 and 2 complex conjugates, but the 0 corresponds to the current source, that is 4 over S. The other 2, the complex conjugate, are eigenvalues of the rest of the circuit. So our circuit is underdamped. And we write that this circuit is underdamped on account of 2 complex conjugate eigenvalues. And that is the answer to part B with its justification. In the paper, I would have written also the values of the 2 eigenvalues as part of the justification, not only words, but numbers as well. Now we go to part C, finding the voltage in the capacitor, which is V1, as a function of time. We have the Laplace transform on the calculator. Break the object into pieces, eliminate the left-hand side, and we're left with the Laplace transform. But x is S. We need to change the independent variable of the calculator in CIS back from V1 again down to X again. Okay, enter, and there you go. You see the X on the top. X is the independent variable. Check that all the ready buttons in CIS are cleared, and we are ready. Calculus, differential, inverse Laplace transform, and that is beautiful, but most of it on the left hand side of the screen cannot be read, so we break that object into pieces over and over and over until I can see all the terms that are added in that expression. And the first break object into pieces gives us that we need to multiply by -1. Let's see, here it comes. Yeah, you see 1 negative? Well, let's delete that, and we will change the sign of every term that we're going to add. So it begins. Break object into pieces. We have the first one that we need to multiply by -1. Swap, and break object into pieces. And now we have the 3 terms of the voltage in the capacitor as a function of time. X is time. We need to multiply each one of the terms by -1 before we write them down to paper. Let's check that we didn't miss anything. 15 over 2, because e to the 0 is 1. And then negative of this term over here. Oh, there is a 0 missing here that'll need to be corrected. I'll correct that momentarily, all right? Here is 0. And then multiply by e to the -70, which is 7x in here, times sine of t, root 15. Here is x root 15. Negative, you say, why negative? Because we're multiplying everybody by -1, remember? That is what we owe the calculation. And that is all. Thank you very much. That is the end of the solution of parts B and C of question 3 of the 3rd midterm.